Hello and welcome to the 19th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. We were in the middle of a very important notion, namely behavioral controllability. Yeah? So I'm sure all of you are aware of the idea of controllability as far as state space systems are concerned. Yeah, but that kind of puts in question the of philosophical nature, that is controllability a property of systems or is it a property of its representation, right? This question also did arise when we did this elimination of state variables, and we found out that a system which has two systems which have exactly the same transfer functions, but when we look at their different state space representations, yeah, the behavior that we obtain in one case is a smaller behavior which is controllable, and in another case we obtain a behavior which is a bigger behavior. So and we saw that we sort of hinted towards the fact that this bigger behavior actually is an uncontrollable behavior as a behavior, right. So we were in the middle of proving algebraic conditions that can tell us whether a given behavior is controllable or not. Let me remind you what the definition was. The definition of behavioral controllability is based on patchability. So given a behavior B which is linear time invariant and given by ordinary differential equations with constant coefficients, constant real coefficients, if for all pairs of trajectories. So B is said to be controllable if is said to be controllable if for all pairs W1 W2 in the behavior there exists, and one more thing, and for all tau bigger than 0 there exists a W which is also in the behavior such that W matches with W1 for all t less than or equal to 0, and it matches with W2 for all t bigger than or equal to tau. If that happens, then we say that the system is controllable. Remember, we actually drew a picture also of this situation which describes what controllability, what this definition is in terms of pictures of trajectories. Then we started proving. I started saying that I said that we will prove several equivalent conditions for controllability of a behavior, which will help us test behavioral controllability given the equations, right. So let me go back to so this is a very important page that will be coming back to again and again. So in this page what I will do is I will write this series of conditions, one implying the next, right, and then I will close this chain so that all of them will be equivalent to each other. So first link of that chain has already been proven. Controllability should imply that the behavior admits a kernel representation which is factor left prime. Remember what was factor left prime? The definition of matrix being a polynomial matrix being factor left prime is that given this polynomial matrix, if I factorize this into a square factor times another matrix of the same size as the original matrix, this original matrix is said to be factor left prime if it is already full row rank to start with, and any factor that you pull out must necessarily be a unimodular matrix. Okay. If that happens, then it is called a factor left prime matrix. And we saw that if we have a behavior B given by kernel of R psi, where R psi is not factor left prime, then there exist trajectories which are not patchable. which means V is not controllable. How did we do that? Let me recall quickly what we did there. So, because it is not factor left prime, I can factorize. So, I will write R xi as a factored, as a product of f and R naught, and this is not unimodular, which means it is a square matrix whose determinant is non-constant, right. So, it has a polynomial, which means this behavior is a non-trivial autonomous behavior. Okay. Furthermore, we can now take a W which is in the kernel of R xi, which is my original behavior, such that W does not belong to the kernel of R naught, and we argued why should that be true. So, we have a non-zero W. So, we have a W in the behavior such that R naught xi acting on W is non-zero. Okay. This non-zero trajectory is what we call V. Obviously, because R xi W is equal to 0, we have this equal to f xi R 0 xi acting on W, which is the same as f xi acting on V, and that is equal to 0 because of this, which means V must then, so this V must then belong to kernel of f. Okay. Right. Now, suppose the system was controllable. Assume that this is controllable. Assume B is controllable, then that implies there exists a W tilde in B such that W tilde T is equal to W T for all T less than or equal to 0, and is equal to 0 for all T bigger than or equal to some tau. Take any old tau bigger than 0. Okay. But then notice what happens to this. What does this mean about this W tilde? Make R0 W tilde act on make R0 xi act on W tilde. What is this? Call this V tilde. Okay. What do we need? What we know about V tilde? V tilde must certainly belong to kernel of f, isn't it? Because W tilde belongs to the behavior, and R0 W is R0 acting on W tilde is defined as V tilde. So, when we multiply this by f xi, when we make f xi act on this, that is f xi V tilde, this must be 0 because W tilde is a part of the behavior, correct. So, that means f xi V tilde is equal to 0. So, that is why V tilde must belong to kernel of f xi. Now, notice what has happened, but the moment we say that V tilde belongs to kernel of f xi, we immediately get a contradiction. Why? What is V tilde T for T less than or equal to 0? This is the same as R0 xi acting on W tilde for T less than or equal to 0, but W tilde has been assumed to be W T for T less than or equal to 0. So, this is R0 xi W T, right, but R0 T is V. So, this is V T, it is a non-zero trajectory, in the kernel of V. Okay. And for all T bigger than or equal to tau, V tilde T must be equal to Notice V tilde is defined as R0 times xi, R0 xi acting on W tilde, right. This is equal to R0 xi W tilde for t bigger than or equal to tau, but W tilde t for t bigger than or equal to tau is assumed to be 0. So, this is 0. So, that means this is also 0. So, here is a V tilde t which belongs to the kernel of f xi, which is, remember, is an autonomous behavior, right. So, here is a non-zero trajectory in an autonomous behavior, which for t less than or equal to 0 is some trajectory, and for t bigger than some tau is 0. Yeah, this entire thing is belonging in this kernel. Is it possible? We have already seen that within autonomous systems such patching are never allowed. You know, if it is an autonomous trajectory, its value, its trajectory gets completely determined for all time the moment you know its value and its several derivatives values at this point, at a single point, right. Or rather, if it is an autonomous trajectory, equivalently you can say that if you know it on an open set, then you know it everywhere. So, like for example, here if I take an open set in the open set which is in the region t less than or equal to 0, in that open set if I know this trajectory, then this trajectory should continue to be this trajectory, this autonomous trajectory, or if it is here, then it should continue to be 0. It is never possible to patch the two, because it's within a autonomous behavior. So, where did we get this, where did this contradiction originate? It originated from the assumption that B is controllable. We assumed B is controllable, that is why we said that, you know, two trajectories Wt and 0 within the behavior, we know that they are within the behavior. So, there should be a W tilde which patches these two, which matches with the first trajectory for t less than or equal to 0, and then should match 0 for t bigger than or equal to tau. That implies that there should be a V tilde which matches with V in the past for t less than or equal to 0 and is equal to 0 in future, that is t bigger than or equal to tau. Yeah, that is a contradiction, because it says that patching is happening within an autonomous behavior, correct. So, therefore, what we had assumed must be wrong, that is what led to the contradiction. So, therefore, B cannot be controllable, B is not controllable. Okay, which then means the implication that I had written here on this very important page, remember. So, we have proved it contrapositively that FLP, if the kernel representation is not FLP, if a kernel representation is not FLP, then it cannot be controllable. So, controllability should imply that it is a factor left prime matrix. Okay. Now, the next link in this chain of arguments is the following. So, if we have a factor left prime kernel representation matrix, yeah, then it must have the following property, that the row module R, remember the row module of a kernel representation, it is just the row span of the kernel representation matrix, of a kernel representation matrix, which is uniquely defined, uniquely associated with the behavior. The row module is what is known as reflexive. Factor left prime would imply that it is a reflexive row module. What is meant by that? Let us try and explain what it means. Reflexivity. So, we start with R, and from R we go to R perp. What does that mean? It means I am finding out a maximal right annihilator matrix from that given kernel representation matrix whose row span is R. Okay. And then I find out a maximal. So, because of Noetherianness, this R perp, which is a column module, that column module will also be finitely generated. So, I will be able to get a matrix whose column span is equal to R perp. Yeah. Let us call that matrix also equal to R perp. Okay. And then I find out maximal left annihilator of this R perp, which is R double perp. Yeah. This is maximal left annihilator of R perp. So, see the process. We start with the row module, we obtain its perp through this maximal right annihilator business, call it R perp, whose column span must be equal to R perp, and then do the double perp, perp of perp. How do you do that? Obtain maximal left annihilator of this R perp matrix. Okay. Now, reflexivity means that the two are equal. You can check in general, this is what we have, anything that is here is already in here, but sometimes in many cases there will be things which are here which are not here in general, right. But reflexivity would mean R will be called reflexive, R is called reflexive if the two are equal. Okay. Now, recall my next chain. My chain says that factor left prime kernel representation would mean that the row module is reflexive. Why is that so? So, I want to prove that R is factor left prime, or I should use R xi. Yeah. R xi, a kernel representation matrix, is factor left prime. That should imply the corresponding row module R is reflexive. Why is that so? Okay, let us see. Okay. So, I have this R xi, and from this guy I obtain its maximal right annihilator, and I call it M xi. Okay, the one that I was calling R perp xi, let us call it M xi. That is the maximal right annihilator. Okay, and then from here I obtain its maximal left annihilator of M xi, and I call it, let us say, R naught xi, maximal left annihilator. All right. So, what does this mean? It means that what is this MR, what is this maximal right annihilator? Well, any M xi, let me fix the sizes, then it will be easier for us to discuss. Yeah. So, look at this R xi. R xi is a matrix of size R G cross Q. Okay. What is this M xi? How do I get this maximal right annihilator? I am sure you will be able to guess it, because we have already discussed how to do this maximal left annihilator business. Any M xi vector of size Q cross 1 xi such that R xi M xi equal to 0, for all such M xi we should be able to find, some what we call it, let us say P xi, such that size we will fix such that M xi P xi is equal to M xi. That is the meaning of maximal right annihilator. That is, every M xi that satisfies this equation must belong to the column span of this M xi. Okay. And then when we find out R naught xi, what is this R naught xi? R naught xi is such that R naught xi is such that any R xi that satisfies R xi M xi is equal to 0 must satisfy the property that R xi belongs to the row span of R naught xi. That is the maximal left annihilator of the maximal right annihilator. Okay. So, by this it follows that rho span of R naught xi must necessarily contain rho span of R xi. Why is that so? It is very simple. You see, by the very construction R xi m xi is equal to 0, right? Yeah, that is how this has been formed. Is the maximal left annihilator, maximal right annihilator, m r a is the maximal right annihilator, right? Every vector that is that multiplies to r from the right that produces 0 must be in the column span. In particular, all these columns are in the column span, right. So, therefore, this must be 0, this must be equal to 0, which then also means that every column, sorry, every row, I should write, every row of this matrix R xi, yeah, every row satisfies every row, let me call it, let us say, how do you call it, let us say R what R I xi, that is the ith row, yeah, say R I xi must satisfy R I xi multiplying m xi is equal to 0, yeah, from it follows from this equation itself. So, then every row is of this type, no, every row of R xi is of this form. By the very construction of R naught, then it follows that every row of R xi, it belongs to the row span of R naught xi, isn't it? And that is why row span of R xi is contained in row span of R naught xi. But about the other containment we are not sure yet. Yeah. Now, notice something funny can be written from here. Notice every row of R xi is a linear combination of the rows of R naught. So, for the first row I take those linear combination coefficients and put them here. For the second row I take those linear combinations and put them here. Likewise, I put all these linear combination coefficients and form this matrix, right. So, in that case this and this will satisfy this equation, right. What are the sizes though? Notice I have assumed that R is full row rank, because I have assumed that it is factor left primes obviously, and without loss of generality we can assume that they are full row rank. So, R is full row rank. So, if it is G cross Q, then the rank of R is equal to G. Then I obtain its maximal right annihilator. What will be the rank of that? By the variation of rank nullity theorem, rank of M must be equal to Q minus G, right. Once again applying rank nullity theorem, we will have rank of this guy to be equal to Q minus G, which is equal to G. So, R 0 also has the same rank, right. So, we can make it full row rank without changing the row module, which then means that R 0 is size G cross Q full row rank, this also is size G cross Q full row rank, which means this must be a square matrix G cross G. Call it F xi, call this square matrix F xi. Then what do we have? We have a factorization of R. We have a factorization of R given by R xi equal to F xi into R naught xi, isn't it? Right? Okay, let me write it a little clearly. Okay. But what we know about R xi? R xi is factor left prime. This is a factorization. So, necessarily this guy must be a unimodular matrix. Okay. Now, obviously from this very construction it follows R is contained in R naught, correct, because every row of R is a linear combination of R naught. So, row span of R must be contained in the row span of R naught, which is R naught. Yeah. Now, because it is unimodular, I also have R 0 xi equal to another polynomial matrix F inverse xi times R xi, is not it, which then means every row of R naught is a linear combination of rows of R, which means the row span of R naught, which is the scripted R naught, must be a submodule of scripted R. So, we have both containments. So, therefore, we must have R is equal to R naught. Look at the definition of reflexivity. Reflexivity says that, what is the definition of reflexivity? Start with a module, why did it go? Yeah, start with a module, look at its maximal right annihilator, which is the R perp module, call span of the MRA. Then row span of the matrix of the MLA of the MRA, right, row span of the maximal left annihilator of the maximal right annihilator, that is the double perp, and that must be equal. So, in our case this was R naught, and that is what we have shown, that R naught is equal to R, which means this matrix. So, this row module is reflexive. So, we started with FLP and we have shown that this is reflexive. So, we go back to our very important page, namely this one. Yeah, controllability implies FLP, FLP implies R is reflexive. Okay. What is next? Next is the following: we will prove that if R is reflexive, then B admits an image representation. This is fantastic, is not it? So, let us see why should this be true. Let us see why should this be true. This is fascinating. What I am saying is, I have a behavior given by kernel of some matrix R xi, and I am assuming the row span of R xi, is reflexive. Okay? Then that should imply that B admits an image representation. B is equal to image of a polynomial matrix. Why is that so? In fact, we can construct its image representation. How do we do that? Okay, think about this. Suppose there is a system which has a kernel representation, there is a behavior which has a kernel representation, and suppose it also has an image representation. So, every W must be equal to m xi acting on L, where L are arbitrary trajectories. That is how you get the image, no? L are arbitrary. Okay. Now, notice, if this equation, okay, let me use the eraser so that I can put this equal to here. If this W were to satisfy that R xi W is equal to 0 for every W within the behavior, I must have R xi W equal to 0. That means W must be in the kernel of R xi. Then I must have this equal to 0, but for which L? For all L, is not it? Because I am saying for all W that satisfies W equals m xi L, this must be true. And how do I get all W? I get by plugging in all possible L's, but L's are free. So, therefore, the moment I insist that W must belong to kernel of R, I must have this equation satisfied for all L. So, let me rewrite what I am saying. I am saying W is given by an image. If W is also so if this is my behavior, collection of all W such that W is equal to W is in the image. So, W is in the image, sorry, W is in the image. Okay. This is my behavior. If B is also equal to kernel of R xi, then I have R xi M xi L equal to 0 for all L in C infinity, yeah, of proper size, of course. Now, notice what does this mean? If there is a polynomial differential operator that annihilates every possible C infinity function, then what can you say about this operator? This operator shouldn't it necessarily be 0 operator? Only the 0 operator can annihilate every possible trajectory. Yeah. If it is a non-zero operator, then it will fail to annihilate at least some trajectory, isn't it? But because it annihilates every trajectory L, then that means this must be the 0 operator. Okay. If this is the 0 operator, so that means whenever we have a kernel representation and we want some image representation for it, then this is just this is a necessary condition that the image satisfies this equation polynomially. This is something that does not have to mean that xi is a differential operator or anything. This is just should be true polynomially. Yeah. Okay. So, our proposition was what? Our proposition was that okay, we want to show that R is reflexive. I want to show that it admits an image representation. As I said that I can construct this image representation. So, I will just tell you how to construct. Why is this how why is this why is it guaranteed to be the to be an image representation of the given behavior is something that we will see in the next lecture. So, the construction is as follows: look at R that was given to you, obtain its maximal right annihilator, call it M. We will show that kernel of R would indeed be equal to image of M provided M is reflexive, provided R is because R is reflexive. Okay. This and many more, the consequences of this result is something that we will discuss in the next few lectures. Okay. Till then, bye from my side, take care.